Welcome back to our lecture 3 on Apache Spark for cloud applications. Now we have the second part where we look a little bit more into the library support of Apache Spark. So this is, of course, a very important part of it. The runtime that we have seen, the core of Apache Spark, is very powerful. That was part of part 1, where we discussed a little bit that it's a very nice reliability part of it. We can define very nicely, in Python, elements to be distributed automatically without even, planning for parallel, for programming in parallel. We have just a typical way in Python how to program. And then there's this interesting driver application that cuts down everything to directed acyclic graphs and then builds from their tasks. And with the help of the scheduler, can actually then leverage lots of these executors. What's a bit missing in the first part and what we will explore in the subsequent lectures is then the data part of it. What is a bit left out is, of course, you want to schedule these tasks where the data is, right? So you need a specific distributed file system that is actually shrouding your data sets in terms of terabytes across a very big Spark application. So doing this all in one lecture proved to be a bit too tough. So basically we take step by step, basically these parts. Now we have a bit more the execution into mind, and we will come in subsequent lectures, lecture 4, lecture 5, and so on, then much more on the data side of things. When we look at MapReduce, how we basically then have different blocks in the data distributed, and so forth. So the second part today will be more libraries for Apache Spark. And let's look a little bit, what are these libraries and where we can basically, see a difference in Spark. This is not that you have to use these libraries. That's an important part. And I think that's good to reflect on the question we had in the beginning. There was something like a question, could we leverage GPUs? You can leverage GPUs, but you need the certain algorithm leveraging it or the library package leveraging it. So for instance, what you could see is Apache Spark, it can also be used by using, for instance, TensorFlow, PyTorch, other frameworks, even scikit-learn if you want, on top of that, to then basically use Apache Spark runtime to some degree. On the other end, you also have to see if there's an algorithm like logistic regression or like some other machine learning algorithm. The distributed nature means you also have to have an algorithm that is distributed in parallel. So this will be becoming obvious more when we go to deep learning, machine learning in terms of really high scale, using deep learning then across very, very big numbers of CPUs and GPUs, where the algorithm needs to, of course, also, basically distribute the gradient updates of the weights of the networks. We'll talk about this then in the lectures. So from the native support of Apache Spark, we have essentially these 4. It's Spark SQL, Spark Streaming, Machine Learning, and then Graph Problems. In a way, you would have said that in terms of data, you have all the key problems or key challenges where you would use data with processing tackled by these. As I said, a little bit out of this is now deep learning and so on. This is really specialized packages where it makes no sense for Apache Spark to redevelop them, rather reusing them and then put them on top of the Apache Spark runtime. But this has also limits, I have to say. That's why there are other kind of scaling frameworks like Horowat or PyTorch inherently has a so-called DDG that is then also enabling scaling. So in the one respect, you don't need Spark then even. You can use these frameworks natively. So when I look now basically on the different, kind of ideas how you use it, Spark SQL obviously stands for the structured query language. Have somewhat used that already with relational databases. Usually, I think should be 101 computer science these days, more or less how you have a very nice table, very homogeneous, basically stored files and extract. Of course, there's lots of support, assuming you have a very, very big Oracle database with terabytes or so. Then Spark Streaming, we will look into this in lecture 11, so very, very late, and even in later lectures in 16 and so towards the end of the course. Admittedly, a quite interesting topic when you can, for instance, not store all the data because it's too much. Think about the square kilometer array when I said 1 petabyte every 20 seconds. Right? The question is, do we really need to store all of this 1 petabyte? Or can we not, in the stream of data, when we work on it, filter the data according to some noise, can put, a focus on certain areas and store that and get rid of, let's say, the 1 petabyte and just store 200 terabytes. This is done at CERN, for instance. Someone knows CERN, maybe, with a Large Hadron Collider, right? This is the same way. They have a big collider. When they do a collision, not every data is stored, right? There are huge filters that filter out the data and then store a little bit of it, which is still big data, admittedly, but it's not the complete data from the Large Hadron Collider. So it's a common practice that you look at the stream and filter things out where you know already that's noise that is out of my areas of concern and so forth. Could be different things, application dependent, and we will talk, of course, in later lectures on it. Machine learning libraries, of course, for us here in the course, also quite interesting. We have used it already a little bit with a logistic regression, if you remember, from the PySpark runtime, but also your assignment will look much more deeply into MLlib. There are lots of different implementations, from recommendation engines to random forests and so forth. We will not tackle all of them in the course, but some of the algorithms, I guess you will learn, hopefully in the machine learning course. You can also use them within Spark, like for instance, random forest, which is still a very interesting, nice, sweet machine learning algorithm. Even with deep learning around random forests, we use them still heavily, especially if you don't swim in data, right? That's the important part. You see basically the GraphX, also the graph algorithms. There are different frameworks around it. And also we have to say Spark often is competing with many of these implementations, which are native implementations basically of these problems, like Graph here, Impala for SQL, Storm, Apache Storm for streaming is also quite known. But the beauty is, of course, the Spark and the runtime, it's already memory optimized. It has this reliability inside, lots of basically positive features that you just basically can give to any data problem. So in the end, you leverage a lot of this in the Spark runtime, which suggests this big part here. And then, of course, you put just a little bit on these different libraries on top and compete then with these frameworks. In this sense, you're usually very much faster because, you have the memory benefit, while many of those don't really leverage this memory optimization. Or if one small aspect in your graph is failing, then you have to recompute the whole graph. While Spark tries with this kind of different task to resubmit just where the error was happening. So there's some different levels where you can really leverage this in memory computing on the one hand, but also this reliability, this RDDs that we also saw a little bit in the video. So one example, and I think it's a quick walkthrough here, how you can consider how that works. Again, the idea how you, of course, program it is very beautiful. You see that here, Hive is another open source tool, usually optimized for SQL. And you have a so-called SQL string, we call it, select star from a table called people as an example. And then basically on these results that you get from this SQL query, you have some names, and then you map basically the names to a certain element of a name, which you have then basically in this people. But you see directly, it doesn't matter how big the table is. It doesn't mean basically to say we have to communicate, hey, with the core A or core B, give me this people, give me that people. If you, let's say we have a big table with, let's say, 1 million of customers, we don't know any of that. So basically, somewhere in this Apache Spark runtime, the runtime has already replicated all of this. There are a couple of nodes that have maybe just 1,000 people, right, from this million, but many of those, and the Apache runtime will now make sure of distributing this, which is a little bit explained here. They could be also here and there in different sizes. So some maybe nodes take a bit more people and so on. And the beauty again is that you don't really see that, right? You just implement typical Python in serial, and it will be mapped again to the directed acyclic graph and uses HiveQL here basically. And by doing so, again, if you would implement this in Hadoop, which was a previous, let's say, Apache open source tool for it, you would have lots of work to do of combining it with Spark SQL. Basically, then you have the iterations much more quicker. Especially also if you think about relational databases, you again and again maybe have the same information queried. So cache, memory will play an important role of having always a kind of homogeneous data. So this is a very nice idea of really scaling up, especially for relational databases. Of course, very optimized for this. If you have, let's say, NoSQL, have you learned about this? Maybe NoSQL data set? Okay. So there, of course, SQL has its limits, right? And there's another support for that, which we also will do actually in later lectures when we talk about more NoSQL stores and those. Here's an example in an application how that would look like. You would have, again, the PySpark runtime to basically import this. You have this library SQL, as you know already from basically Python. You have to import certain functions. certain types on it, a row and so on. And you see here quite with a data frame that we already talked in earlier, we can register some interesting table and work on tables very nicely, basically then with this whole idea of SQL and so on. And this is all basically possible by just, using this automatically under the hood with Apache Spark, while usually you would have quick problems when you do one Oracle database, which is very centralized and so forth. So very scalable approach, that's what I'm saying. However, what is missing a bit is we have to prepare all of that. The database has to be, of course, once loaded into the data space of Spark. Hence, we talk about the Hadoop distributed file system again. We have to basically configure how many replicas there should be from the whole data. So how many blocks will be separated. Again, what we focus here is a compute part, how you program it. We will come back to the idea how this is now basically stored in terms of data. But of course, for the programming, you see it's quite nice, especially here again, when you think about you're in the company, you want to have some sentiment analysis about your company, you have a Twitter stream, you're not interested in the whole stream, you want to just filter out where are tweets about my company or where are tweets about me. So basically you can do this with a couple of lines of code again, right? While assuming that Twitter, the whole way, it's just 300 characters basically per tweet, but of course you have millions and billions of those, right? And here the Spark runtime again basically helps you a lot by programming this very much quickly with a couple of lines with a stream coming in, and then basically can already filter out what you're interested in, can maybe drop it to file and you will get more deeper in. And even if a node crashes here and there inside this, right, basically, well, you pick some of which are you're concerned, it will be resubmitted on that data or on this tweets where it crashed, will reanalyzed and will put it also basically in the kind of analysis again, which is again something of which you otherwise you would have to start again the whole job on the whole stream. Something also you don't want to do because Twitter streams quickly can elaborate to terabytes of data, right? Coming in. There's also Firehorse, a specific Twitter API. If you have the normal data from Twitter, it's very restricted. There's not much data, but there's a cost basically you can put to it and then buy more tweets, which are quite interesting and valuable for companies to analyze. And here we will again look in this in lecture 15 more explicitly how we can filter. This just should give you an idea of the power that Apache Spark has. Always thinking about there's already this nice runtime underneath, right? And you have this runtime to your disposal. All what you have is now think about your data and your concrete logic, what you want to filter out or whatever you want to do. And then you see with a couple of lines in Python, you already get the full power of a whole cluster of parallelization, basically. And you go on and on. Basically, in the machine learning libraries, there are also no surprises. It's pretty easy to actually implement there. Here's an example of the so-called k-means algorithm. You know that maybe from the machine learning course. Usually it's very early in the course. It's not a really powerful clustering one, which means basically it has problems here and there. We usually use rather DB-scan, which also can detect, convex problems and stuff like this. But in the end, it's a very pretty straightforward one. Particular problematic is here that you have to pick the K. So you have already need to have an indicator how many clusters there are, what we in practice when we work with real data don't have. And DB-scan and other more powerful algorithms usually, find that themselves. But still, there are different implementations in the MLlib. K-means is one of it. Logistic regression already showed you. But as I said, also for classification, you would have random forest. Random forest just basically grows 1,000 trees. Decision trees are usually very prone to overfitting. They are very bad, basically. But if you use thousands of them, right? So grow 1,000, which brings us to random forest, 2,000 of these decision trees at once, and use bagging, boosting, and other mechanisms, then they're very powerful, right? And then basically outperform maybe even other algorithms like support vector machines. So basically, there are some shortcomings in this MLlib, as I was alluding to. Support vector machines we use in practice as well, very much, and have extremely good results in remote sensing and so on, because it's a quite robust method. You just have a couple of kernel parameters and the cost function to see, or a cost of error you allow. And these implementations are not there because it's quite hard to have the quadratic optimization parallelized quickly. Interestingly enough, at the end of the course, I will show you that basically then in the quantum world, we use SVMs quite nicely, basically with a quantum computer, and there the results come back in a second, right? Which shows you also the advancement of computing and also the future. Yesterday at the conference, we had also a quantum session, so lots of our activities are going. Those that have seen my talk, the last lecture slides basically was also about our work on quantum annealing, which is really beautiful for machine learning solving optimization problems, right? And while here in the cloud, we have lots of iterations. In HPC, we have lots of iterations. The quantum computer comes really back in a second with a solution. And of course, this is basically the news of using quantum qubits and entanglement, which we maybe also offer as a course at some point in time, maybe here in the future at HOE. Good, but of course, let us come back to Spark here. So clustering, there are regression problems to be solved in classification. This is all beautiful, supported. There's one part that we will allude to also in later lectures from Shadi, one of my PhDs. He will look this a little bit into recommendation engines. So this is also quite nicely supported there, basically in the MLlib, because it's also a problem that you can nicely parallelize, so to speak. What you have basically, recommendation engines in terms of you look this video, then basically you probably also look that and that video. But this comes also in later lectures, not all in one lecture. Let's focus here a little bit more on the libraries that we have. And the machine learning library is certainly one we come back to again and again. Another thing I wanted to mention, machine learning context, which is important here. I'm not sure if you have done lots of validation maybe in the machine learning course, like parameter optimization, like hyperparameter optimization of sort. Of course, this is a topic which is also beautiful on Spark. You can basically run different configuration parameters in parallel on the cluster and pick the best with the best performance. That is one way of using also the Spark cluster, not with training one single model, but you run maybe 10 or 20 models with different parameter optimizations. We come in subsequent lectures also to this fact, but this is of course another idea how you use the parallelization of such a cluster. In rare cases in machine learning, you know exactly the configuration parameters. And for model selection, which is validation doing, you pick the correct model basically with all the different parameters. Their parallelization helps you also hell a lot. Good. Example here of the logistic regression we had already. It's basically the idea that we had the last time, if you remember. All we did is basically having the same linear learning model we had before when we had the flowers. Here we pushed it then into the pass or fail, the food inspection, if you remember. Or basically also, will they basically 0 or 1, will they do a bank deposit or not a bank deposit? All the same problems mathematically by looking at the data and then mapping it to 0 or 1, pass and fail, and so forth. So in the end, the logistic function is then the signal basically you use. We have basically used in the beginning just a step function basically with -1 and +1, but with a logistic function, you have a bit more elaborate, but still a much more smoother way of really doing the classification categories. And this brings us then basically to the idea of optimizing this step by step using, for instance, stochastic gradient descent, as we discussed also the last time. This is the most computing extensive because you always take the derivative of the current function that you have and basically move yourself closer and closer basically to the minimum, which hopefully is a global minimum that you not really can ensure. It's often a local minimum in this error space. So it takes really iterations over iterations of learning from the data to go in that direction. And by this, improving the model performance, hopefully, but it's a very simple algorithm, so to speak. There are much more nowadays like Adam, which also take momentum, Nestref momentum, also speed downhill into account. And we will revisit this again in subsequent lectures again and again. But of course here, this is what basically also then is nicely performed in the cloud, because this can be quite some elaborate process to find the minima. And of course, finding the minima is then also dependent on which hyperparameters, which other parameters you pick. Hence, the error surface looks different. So you want to maybe use with different configuration parameters the whole cluster and come back then with the best one from the parameter perspective. So that's how you would use it as an example, for instance, and where the computational step is, of course, again and again. Of course, later then when we go to deep learning networks, this is just in, let's say, in one key small part of it, when you have the whole neural network, you have to do this a lot of times and backpropagate the error through the whole neural network. Here we have a very simple linear learning model where this is, of course, not so intensive. Hence, in this smaller logistic regression setup, you here and there are still okay, maybe by using scikit-learn on your laptop. The trouble starts when you have to analyze petabyte of data, then probably your memory is quickly at the end, or using R could be also an option. But of course, then as soon as you talk about big data, you have some problems. Right, still some performance characteristics, logistic regression, that what we had in the earlier lectures, compared again to our famous Hadoop, which everything dumps to disk, right? Every iteration, the intermediate results of the model with all the parameters dump to disk, read from disk for the next iteration. So that makes it very slow. As we learned, Spark is much more clever in this by using, of course, memory, and can significant, of course, improve the process. And why is that so? Because the data remains the same, right? The iterations of the machine learning model is just always the same data. I go over the same data, do weight updates to updates on my model, always the same data. If the data already is in cache, especially for machine learning, you can, have lots of benefits. On the other end of this is the other end of the scale, you really have to think about. Spark then costs hell a lot of CPUs with memory, right? So in order to get this benefit, you really have to have a memory machine. Right, and I think these iterations are just beautiful, essentially. That's what we're saying for Spark, which was one of the limitations in Hadoop and made Spark so successful. And again, as I said, there's basically recommendation engines that you can easily program with MLlib on scale, right? No matter how many videos or whatever you want to recommend, movies, etc. you want to do, this alternating least squares, that's quite working. I said already, this, random forests are very well supported. Clustering, there are several approaches. Frequent pattern mining, FP growth, and things like that are very good. And we could come to this in actually, I think, lecture 11 and others. And of course, here in practical lecture 3.1, there will be also a couple of them I will demonstrate on Tuesday. Let's come the remaining part also to the GraphX library. I don't do so much graph. Basically here, mostly also because it's quite a complex topic. It has something to do that the world is unfortunately not always a table. So many things we have in physics, many things we have in real life are more or less a graph structure, which means there's a different idea of an algorithm that you can fire on it. And in this sense, graph could be a whole lecture series, right? So alone from our race project, what I was talking about at Harper, for instance, we have lots of these problems with graph neural networks these days, which basically preserve a little bit the low connectivity, but are not a homogeneous network or table, so to speak. In this sense, you can see lots of these problems where you need this graph support and graph library that is actually supported by Spark also quite nicely, again, with the idea that you don't want to know the details on the lower level in the whole Spark cluster on the CPU distribution. You rather operate on the tree, and then automatically the tree will be scaled out to the, let's say, lower levels that you have on the cluster. One web application, just to remember you maybe what is the idea of a graph, and also think of, what is the benefit of, really using this, is a very simple application here, which is this PageRank technique. So the idea of thinking about how you're ranked on websites is a problem which is essentially not really a big table where you think these websites look to that. It's rather something which includes weights, or is the really powerful websites are looking or pointing to your site, right? You can have 5 web pages of your friend that actually look to your site or link to your site, or you have HowE or Reykjavik University pointing to your site. There's a big difference in the algorithm. I show you a little bit, but it also captures away the message that there's some computing happening depending on basically the ideas that come in from the different, let's say, edges, and from the kind of idea that you have with the interconnectivity. And the web is, of course, if you want to compare it a little bit again, like our decentralized structure here, the perfect structure for it. And here, why we should press it in SQL, why we should press it in a more normal table. If we have a kind of native support with this, with the MLlib, let's just go ahead and use it. So let's go through a simple idea of thinking about this, which is, let's say, one which was very famous in for old days, making actually in times of Google Beta. Do you remember still this? Some of you maybe. I remember still using Google Beta, funny enough, and nobody would said, you know, buy lots of stacks for Google or so, or stocks for Google. So this was an interesting thing. And the search algorithm was all they had, right? And this was a little bit this PageRank and the idea. Now Google is, of course, you know, has lots of different sub companies and so forth. But that's how it goes sometimes. And they were very smart in leveraging this MapReduce technique and the, let's say, Spark inspired techniques. That's why we will look back on Google technology, also admittedly a bit now older ones, but that's how it started basically also. And we will look in this in lecture 5 as well. So because this was just beautifully supporting it. And here you see essentially the concept. So you have lots of smaller websites, you know, which are not so frequently visited. They have probably less weight, but there are some websites that, you know, here are very strong, often visited, have a very big impact in, you know, providing a link to a page. And this is something what you need to iteratively compute now, which is essentially a very, very complex algorithm to do so, but also nicely to be independently computed. That's the interesting part now where Spark comes into the play. And by iteratively going through this, and I gave you here some examples, where you basically have also the contributions of these different pages, where you have maybe an initializations of all the ranks of saying every rank is 0, but already you can see that, you know, this page here is often pointed at, for instance, so that is meaning perhaps something, and, you know, it points to someone. So it might be the one that is often pointed to also points to someone, could then already in our mind, you know, meaning something important. So when you go now through that, you have this update rule, always like basically having the 0.85 times the contributions that you get from the others. And by iteratively doing this, so you can basically come to the same idea like machine learning, where you put a model reducing the error of a cost function or an error function. The same way now you compute the page rank, right? So again, the idea of having it iteratively is here a major point why you can leverage Spark, why you can leverage parallelization, right? If that would be not really an iterative approach and recursive and other elements, that would be much more tough to use basically the Spark engine. So here you have the example, you get the contributions, you have a one page that here you see it gives its full contribution to it. Here you see we point to 2, so we have just half of contribution as for example, which basically then shows you that iteratively by doing so again and again, this is intermediate. Now this would be Hadoop dropping it to disk, very slow, but Spark taking it from memory again and doing the next iteration. And then by iteratively doing though, I mean, this is not really rocket science here now, small numbers, but think about that the now internet is quite huge, right? There we don't have a graph with stand of 4 nodes like I present here, but the same idea is true. And of course, you see through this iteration, there are some local updates of nodes. Only those which are connected give you contributions. It means you can also cut basically the graph a little bit into pieces and nicely parallelize this to some degree, right? And by iteratively doing so, if you want, you can do at home the math, but that's not the idea of this lecture. The idea is just by iteratively doing so, you can get to the page rank, which we already thought in the beginning is somehow clear, because we see here that, you know, this page must be something very important. Many people are actually pointing to it. So this seems to be a very important page. And by having a link from a very important page, we can also imagine that this fellow here, you know, probably gets lots of contributions from it. And that's how basically also Google and others, with some modifications, of course, in detail, but still the basic principle are ranking websites. Today, this is a whole paradigm we will shortly review in one of the later lectures when we go again to Facebook and AdWords and AdSense. Have you already experienced with those, maybe AdSense or AdWords from Google? So all this advertising, how that works and so on. I will have one lecture on this, which basically is then a search engine optimization related techniques. We have that in later parts in our cloud course towards the end. But this is all connected to that. And of course, also something where you can leverage cloud computing a lot. And also how you can finance cloud computing offerings. You see Facebook is for free. They make hell a lot of money through Facebook ads, right? That's their main point. Right, convergence, just to show you some, of course, more important numbers now. I have given you a toy example to look at, which is not very impressive. But now when you think about how many links there are, right? So here you see an example perhaps of having this 322 million links, how you can nicely basically, break that down in the number of iteration and how it converges then to a, let's say, state where the balance is then in this PageRank given. And of course, this is now something where the more million links you have, now Spark will have more impact in the whole iterations where you go to and can then parallelize this quite nicely by each iteration. And here's again a kind of small idea how you can have PageRank on Hadoop. Again, here you see already a little bit where we also come to in the course. It depends on you, of course, how much you want to parallelize. Here you see basically we have number of workers. Just a small feedback also to the video you have seen. This master-slave architecture is basically something you should say that anymore these days. It's called master worker. So the people have strong assumption is having master-slave, right, these days. So it is called master worker, to be honest. But here you see the number of workers, right, that really do the work, do the kind of page ranks, do this kind of small computing. Hell, a lot of small computing we have seen. It's not much. It was a very small formula we have updated, but we have millions of it. And by having more workers, of course, you can do much more quicker these smaller computations. So you see here from Hadoop, again, compared to Spark, we are much more quicker. And if you add, let's say, instead of 30 workers, you add 60 workers, so double the amount of power you can really have. You have then Spark actually being very, very quick. However, notice also, as I said to you, the price matters again in the cloud. If you have 30 workers, you pay the credit card for 30 workers with memory. Okay. With 60, you have the double in price, right? So now you have to judge, is it really necessary as a company, right? Do you think really from 23 seconds to 14, is it really worth giving 30 more workers to the problem? And this is, of course, something where you as a cloud expert then in the companies in research have to think about. Do I really want to invest the money? We see sometimes the speed up is really limited. And if you add now 90 workers, you can already predict that essentially the speed up would be very, very limited, if at all. Something also we will talk about at some point in time, we reach a so-called limit where the kind of overall setup, the communications will basically outperform our parallelization strategy. So here you would probably say, of course, in Hadoop times, yes, that makes sense. In Spark times, you would say, okay, do I really want to invest, double amount of money just to get a couple of, seconds more here, 9 seconds. And this is a problem you see everywhere when you come to clouds and scalability. Of course, in the end, it's in your hands. And the real companies like you have here from Yahoo, Conviva, that's a daily story, what to think, how much more we basically buy in terms of computing. And some applications of Yahoo, they had news pages. You can see the news pages is, of course, very, let's say, nicely parallelizable, right? Take a news page and they want to categorize this new page or basically do tags on it. They basically can do this in parallel. Every new page alone has no dependency with the other. But of course, the end result should be something like this new page has mostly noted sports. So it's probably a sport, news page. Let's make the tag sport. But how you do it, basically, all the different news stories have no interaction. So you just can do it nicely parallel over the whole cluster and speed up. And, use the tools we just discussed, Hive basically for the news stories and the SQL access and basically using Spark. Conviva is then basically around streaming videos. Also there, you can imagine Spark streaming. You can do there lots of features. When you stream over the wire, one is probably known of skipping, for instance, the intro to a certain series that again comes again and again. It's a sort of filter in the stream. But there are lots of different applications. Also maybe switching the stream performance. So when you go from a higher, let's say, resolution down because your network has some trouble identifying that in the stream and then reacting to that. You have probably seen that in YouTube. Sometimes it will go down in the resolution and so on. If your bandwidth is not enough, these things like that you can do. And ClearStory is really also using Spark technology for some real-time product. It's a data-driven product. Of course, there also Spark technology is there. But of course, you're free to Google around. You will see Spark is here and they're really hidden in the features of a product. you see basically these have no exposure of Spark at all. It's in their back office, right? Where they use Spark and on their data. Then, of course, if you're interested in playing around with Spark, the Google Colaboratory also allows it, but of course, there's a certain, let's say, limitation on it. So when you buy Google, Colaboratory access, you get a bit more for $9.99 basically per month. You still have not a big Spark cluster. You can run PySpark on it, and it will basically create you a PySpark session on it. But of course, the amount of workers like 30, 60, 90 is something you cannot get in the Google Colaboratory. So you get a TPU, you get a GPU if you want, and also CPU and so on. You see that, and one part of the assignment will also touch base on that. But of course, this is not really a real big Spark cluster. Still, you can program using the PySpark, let's say, APIs and the libraries, which means you can maybe expand and basically try out some implementations there. And once you're ready with it, you basically port it to some cloud provider like MS Azure or basically others. We'll go back to the Google Colaboratory also in lecture 6 and 7 when we go to deep learning and see there are lots of limitations from speed compared then to real clusters where you see, of course, we have much more performance than just using, let's say, one GPU or so. Still, it's a nice tool, I have to say. Never it was so easy to get computing for free. You don't even have to use the $9.99 per month. But then the trouble, you come a little bit, you don't know what to expect. Sometimes you get a GPU, which is a Kepler. Sometimes you get a version, which is an Ampere, basically. So it's different, let's say, ideas how you basically can get access to GPUs there. But still, it's quite nice. And integration in your Google Drive, that you basically have the data quickly then in your Google Drive. All you need basically is a Google account. That's what I'm saying. And then you can directly start. I'm not sure if you use Google Colaboratory already somewhere in the course. Is a machine learning course using it or Scikit Learning also? Yeah. Okay. Yeah, but it's an interesting tool. As I said, very limited in terms of scalability, but for programming, starting programming is definitely very good. And that's, again, I think all I can leave here on the computational part of things for Spark, right? To get you started with the assignment 1, we will talk about next. But also then in the next lectures, lecture 4, lecture 5, you really have to catch up on the big data things, what it means to have replicas a lot, where you can then push all the computational jobs to. So let us conclude a little bit with a small summarizing video again. Again, the flavor of the course is also addressing machine learning. So the next video will also have a little bit an emphasis on this.
Hi, I'm Matej Zaharia. I'm a co-founder and chief technologist of Databricks, and I also started the Apache Spark project back in 2009 doing my PhD at UC Berkeley. Today, Apache Spark is the most actively developed open source project in big data and probably the most widely used as well. There are hundreds of people contributing to it every year, probably over 1,000 since the project first started, and it continues to rapidly add new features, new capabilities, such as libraries to do different types of analytics. What's unique about Spark at the highest level is that it's the only software framework that combines data and AI. So using Spark, you can do large-scale data transformations and analysis, and then you can immediately run state-of-the-art machine learning and AI algorithms on it. And that's super important for building AI products because AI is only as good as the data that you put into it. It's powered by the data. And so when you have a framework that can do both things and that designs them to work together, you can quickly build the highest quality application. So at Databricks, I personally focus on a variety of topics just around our technical and product strategy. So with respect to Apache Spark, I'm always talking to users, trying to figure out, what are the issues that they're having with it, what are additional features that they'd like to see, and helping to guide the contributions from Databricks in these areas of the open source project. In addition, at Databricks, we're interested in building a unified analytics platform that's end-to-end, that goes beyond the analytics engine. So I'm also thinking all the time about the analytics process in general, how to enable enterprises and organizations to just reliably build data products as part of their business, and helping to design a lot of the key components of our platform that let our customers do that.
Okay. As usual, the disclaimer, I'm not paid by Databricks. But yeah, we break again for 5 to 10 minutes and then talk about the assignment.